My goal of today is to kind of establish this name, quantum system quizzing, and what it means. And that's already, I see it's happening, that you remembered without kind of having the slide on. This is the ongoing work that we do for the past couple of years now in my group with the PhD student Jan Noller and also a PhD student Anne Schroeder. They are in the audience, so if you have technical questions, you can ask them. And also we work with the group of Martin Klisch, who is at the Technical University of Hamburg, and Nikolai Miklin, who is also in the audience here. Yes, idea is the sound and efficient quantum system quizzing. So I want to explain you today why we need this and what it is at all. So it's a new protocol that we came up to answer one big question. And the question is the following. You have a classical user or an experimentalist, which is the same thing, we think, talking to a quantum device. So the way you are talking to a quantum device, you are sending some kind of instructions, or you are setting up certain probes and you want to get answer. And your goal is to test a correct functioning of a quantum computer. Simple as that. Now you can ask, okay, that's a good motivation. Isn't everybody doing that pretty much? How do people do this? And indeed, a lot of people do this. There are many different quantum computers at the moment available either in industry or academia. And people do get numbers out of these quantum computers. So to give an example, there is a development roadmap. And this I didn't update. It's a picture from last year. So they always update. That's an IBM development roadmap. We should be somewhere here. I'm not sure this is happening yet. You can correct me if I'm wrong. But then if you open this web page and click one of these squares, you will get a bunch of numbers about the errors in different qubits, gates. So you see that they give you the gates and they tell you that they have these kind of errors. Then you go ahead and, okay, I don't understand these numbers. Now let me go ahead and look for other quantum computing numbers. You Google what are the best quantum computers with the highest fidelity. Of course, you see a lot of ion trap results. And there also you see a bunch of numbers. Very promising, very, very promising numbers. And there was, let's say, another announcement, breakthrough from IQM quantum computers last year in July, which said that they had a great milestone of 99.9% 2-qubit gate fidelities. This is all great, right? I mean, the story goes on very nicely. Now the first question that we are asking, how do these people get these numbers? What do they actually do? Because in my own experience, when I try to use these devices, these are not the numbers that I see for the applications. So now I'm not saying that these people are lying, but I'm just trying to question how is this happening, because maybe on a systematic level we have some kind of a problem to obtain these numbers whenever you try to certify these devices. And I'm going to come to this terminology also later. So one of the examples, this is the IBM's quantum computer. They are for different generations. Well, that's what I assumed it's happening here, because it's getting better over generations, over 80 to 100 qubits. And they have benchmarked their errors according to some measure. And they say that for their benchmarking, to cut it short, they are using a well-established way to benchmark quantum computers called randomized benchmarking. And I don't know how many of you have heard of randomized benchmarking, maybe. And many of you know probably what's going on. If Jens was here already today, then he knows definitely much more about it than I do. So that's one of the ways how to benchmark these devices and say what are the gate fidelities or some error rates. There are other ways, right? There is a process tomography. Now the process tomography, what it does, it prepares states. It applies the channel or a gate that you don't know. And then it measures this in different bases. And according to this, you learn what a quantum gate was. Well, this kind of approach has a couple of issues. First is that number of experiments required, which we called for this talk sample complexity. This is too high. So if you wanted to do it for 10 qubits with a certain precision of 1% error, you would pretty much take a very long time, 10 to the power 10 number of measurements. So the process tomography has the problem that it's not even scalable. There is no polynomial way of getting data out of a quantum computer. But okay, now you can say on NISQ devices, maybe you're happy to check few number of qubits separately, and why not to use this approach? There is a second big problem. In our opinion, that's a bigger problem actually than this one. And if you think something is a bigger problem than that, you should probably hear what the problem is, because 10 to the power 10 is already a large number. So the second problem is in the process tomography, you have to trust your states and measurements. But how do you gain trust in your states, state preparations? Usually you trust your measurements. But how do you gain trust in your measurements? Usually you trust your states and then you benchmark them against one another. And this is a bit of a chicken and egg problem, which this is a dependence on state preparation and measurement. Shortly in the certification and characterization community, this is known as spam. And if you have spam errors, what it means is that no matter how much sample complexity you have, how many more measurements you do, you get systematic errors from your data, and you cannot reconcile the true experiment with the theory that you wanted to test. So then we want to have certification methods which are spam-free or robust against the spam. Yes, so what are these methods? Yeah, so the first one, I put it separately. It's not spam robust, so we don't like it. Spam robust methods are randomized benchmarking methods, and there are many flavors of it and a lot of people use. There is a gate set tomography that's also spam robust. Both of them are efficient into computing certain characterization of the gates. And all these methods are complete. What the completeness means is that if the implementation of a quantum model, states, evolution, and measurement is close to the target model, what you wanted to implement, the data obtained from the experiment will be close to your desired data. That's something that you expect. If you made in the experiment something correctly, then you should get correct answers. But how about the other way around? And that's where the soundness, the first word in my title, comes in. Are they also sound? Well, the first one, which is not spam robust tomography, is also sound, but well, it's useless in the experiments in the sense that you cannot, for certification, you cannot really put things aligned together because you are assuming what the state and measurement is. So I'm not discussing soundness for the first part even. For the second, for the other methods, the reverse implication that you want to say what a quantum computer does from the data that you obtained, there are no guarantees for that. There are no theoretical rigorous guarantees absolutely available for the certification. Okay, now we have other methods which are complete, sound, spam-free for quantum certification. Well, the first one is Bell test, right? If you violate a Bell inequality maximally, you can say that you have an entangled state which is close to a Bell state. And this is exactly what you see, that you are a classical user interacting with the quantum device. You get statistics out of a quantum device, and from there you can say that I must have had a Bell test in my experiment. There is something which is on a single device. It is prepare and measure scenario. Here you usually put a dimension assumption, and what's happening is that you have certain states prepared in the beginning. So you only, or I don't know if you see this, it's very tiny. You see the, okay, good. You have a state preparations. It's a classical data that you have control over here, here, and here. And only from these statistics, you want to talk about you want to certify the overlaps between the states. I guess David will talk about this in a bit, no? Okay. I thought from your title, maybe you will have the overlaps between. Okay. Then I'm more intrigued about the talk. And the last but not least is a new development. Instead of doing the Bell test, where you have the space-like separation between two parties, you want to replace space-like separation with post-quantum cryptographic assumptions. And if the questions you are asking to a quantum computer is hard enough for it to fake the answers without it doing the correct thing, you will be able to detect it. But that has certain issues itself that it needs too many qubits to implement. Now here we also, not only we have the soundness results, but we only have certain guarantees that if you don't violate the Bell inequality perfectly well, but epsilon close to it, you can guarantee that your state will be in epsilon to the power 4th root of epsilon close to the correct state. In the case of prepare and measure scenario, this looks much worse, scaling. You have 1/16. So that's quite a bad guarantee there. For the case of using the last one, you need just too many qubits. You almost need fault-tolerant quantum computer to implement such a scheme. So that's out of the reach, and such rigorous guarantees are also missing for this case to learn what is the dependency between how well you are doing a protocol from your data and what is actually happening in your experiment. So a lot of people just think that since we have a Bell test on the other hand and such a guarantee, you can go ahead and just learn what a quantum gate you have implemented using the space-like separation. First of all, this is not applicable for a single device scenario when you are talking to a quantum computer. You don't have the space-like separation. Second way you can deal with this is that you can assume, and people have done this, that in IBM quantum computer, you have no crosstalk, and you can play the Bell tests there, but there you cannot really assume that the measurements are not talking to one another, and sometimes you get the data which is even violating the signaling assumptions. So you cannot really use Bell tests for studying the unitaries. Okay, now I'm going to tell you about our method. I hope I convinced you that something is missing in the literature for the certification. The aim is to have a complete, sound, sample-efficient, spam-free certification of a single device. And we propose that our ways, which we call QSQ, or quantum system quizzing, is going into that direction. Now I have a feeling that I'm doing a bit of too much advertising, but I'm not saying that maybe we close all these gaps all the time, but I want to encourage the discussion that such things are needed in the community in order to really put sense into these numbers that we are obtaining from a quantum device. Okay, now let me come to the outlook of the talk. So I'm going to tell you what a quantum system quizzing is, starting from our main idea of how to start with rigorously talking about a protocol that you need to use for certification. And then directly I'm going to go to our results. We will start from the single-qubit simple pi-half pulse gate certification, which itself is not so easy, turns out. And then we will talk about this epsilon dependence and what happens if you have noise. So of course you won't have perfect experiments. And finally I will get to universal gate sets, and then this is for discussions and the questions pretty much. Okay, preliminaries. What happens here is that you have a classical user talking to a quantum computer, and we know that quantum computer and classical computers, in principle, they can solve the same set of problems. Right there, unless you put certain assumptions, let's say polynomial time assumption or something else, they can exactly tackle the same problem. But now we also know that we have a quantum advantage, right? We have algorithms which tells us that you can solve certain problems faster. And this is happening already. You can see that quantum and classical computers differ on something that is called promise problems. What it means is that you have a promise in the input. So for example, Deutsch-Jozsa algorithm is supposed to test whether the function that you have in your oracle is balanced or constant. You are promised that you will be given either one input or another. You won't have some other function. And in that case, you already know that you get a separation between classical and quantum computation. In this particular case, you get a separation in time. in the number of calls that you need to do in order to solve a problem. You can think the same way if you know quantum algorithms, Bernstein-Vazirani algorithms, you are promised to have a hidden string. Simon's problem, you also have a promise there. And then you get this time separation. On the other hand, there are other promise problems known since the early 2000s, which give you separation into memory. And this is what we want to utilize here. So let's consider a very simple example. Let's consider that you are a classical user setting 4 possible set of instructions to a quantum computer. The first instruction is just nothing. You tell a it's an empty set. You are telling a quantum computer just to measure. Second instruction that you are sending, set of instruction is S and S. Like this is just classical label. It's going to make sense later. And the last one is 4 S's. A very simple problem. And the promise problem is the following, that quantum computer or a classical computer, a device is promised that the input will only be this and nothing else. And now the device needs to solve the following recognizability problem. It has to output here the answer yes if the input was this, and it has to output answer no if the input was that. And the question is, how many dimensions of what kind of memory would you need to solve this problem? So you can think about it. I will tell you the answer is in the very nice deterministic finite automaton theory. And here what you do, usually you use the drawing tools. So the drawing tools means the following thing. This is the automaton. So this is the starting state. You enter in this state. If you measure right away, you have to obtain yes answer. Then S, whenever you get S as an instruction, the internal state of the system needs to be updated. And the claim is that this is the smallest dimension you need to solve the problem. So you can think about it. If you get S and S as an input, you transition to no and you output no. If you get 4 of them, you jump back and you output yes. But the claim is there is no smaller way to do this. There is no 2-dimensional automata to solve this problem. Now you can make a problem slightly harder. You can add yet another additional string. The yes answer stays the same. The no answers have also 6 S's sitting in there. And for this, you would need a 4-dimensional automata to solve this problem. It means the 4-dimensional state. So in this case, it would be 2 bits of memory needing to solve it. So this is now a promise problem which can have an increase in a classical required dimension. Now let's see how you would solve it with a quantum computer. Maybe you have an idea already, but a qubit can definitely do this. Quantum mechanically, what you can do, you can start in a plus state, apply an S gate. That's why the instruction was called S. And you can measure in X basis, eigenbasis. And you can look at this will be our solution to the problem. You start in the plus state. If you measure, you will obtain plus. So for the empty one, you call yes. If you jump 4 times around this equator of the Bloch sphere, you will come back to plus. In every other case, you will get a minus, because if you jump twice here or 6 times, you will come back here. So what we get is that qubit can solve certain promise problem when classically you would need a 4-dimensional system. Now you can play this game longer. This was one promise problem. And you can show that you didn't have to start with the S gate, but you could have started with the T gate, let's say, and separation there would be 2 versus 8-dimensional system, classical system. And you can make this separation exponential. Easily, actually. That's very easy to do. But what's very interesting for me is that you can also make this separation infinite. You can have an infinite dimensional classical system required when quantumly you can solve the problem with the qubit. And I think it's a neat example that we don't teach in quantum algorithms seminars, that on promise problems you can have an example where you have infinite separation. You would need infinite dimensional classical system to solve the problem. But of course, for the sake of certification, infinite dimensional separation, achieving this is impossible because you need to have infinitely long input strings to be tested. And our question here in quantum system quizzing is, can we use this advantage into memory and turn it into the certification task? And that's what the goal is, actually. It's a very simple goal. General idea is that have a promise problem and check if the quantum computer gives you a correct answer all the time. And if it gives you a correct answer, you want to learn what is exact internal workings of a quantum computer. And to test this, we have a protocol. So what the quantum system quizzing protocol does, you pick number of n repetitions, you set this promise problem gate sequences and the promise problem, and you sample from these gate sequences randomly according to some probability distribution. And it's a very simple loop. From 1 to n, just pick one of the instances of the promise problem and check if you get the correct outcome. If the outcome is wrong, you reject the protocol. If the outcome is correct, you continue until you run out of the repetitions, and then you accept. So you don't gather any probabilities from your device at all. You just keep running it until you fail for the set number of repetitions. And the question is, can we learn a quantum computation, unitaries or channels just from this protocol? Now I'm redrawing. Before we were drawing things like this. Now I want to redraw it in more quantum information sense. So what we have is that it's up there is a classical user. It's interacting with a quantum computer. And the quantum computer initializes the states. Every time you press a button, it executes certain uncharacterized channel. And then at the end, it's making the measurement. And it gives you a classical outcome. Now, there are two assumptions that we have here. First assumption is that dimension, let's say qubit dimension, is fixed of your quantum computer. If we are talking only about single qubit, or later it will be the n-qubit quantum computer. And there is time independence. So as an experimentalist, you try to always implement, whenever you press x2 is equal to some instruction here or here, you are assuming that this should not matter. Of course, now in the experiment, this might not be perfectly fulfilled, but this is the minimal assumption you need to do in order to gather any statistics or have a Born rule written in this sense, that you have prepared a quantum state, and then you're acting with certain channels according to your input, and then you're getting the outcome. Now, these assumptions might seem a bit stringent at the moment, but I'm going to tell you that they're used everywhere. They're minimal assumptions everywhere, and the other methods like RB or gated tomography, they have much more assumptions on top of that also. So our claim is that without these assumptions, you cannot go very far. And now we have a definition of a quantum model, which is just every time I say quantum model, I mean raw lambda channels and measurements together. So these three tuple together. And our goal will be to learn what these three tuple is simultaneously together only from the promise problems that we had. And now I'm going to give you a bit of a more technical definition of what we mean to learn this model. And we say the following thing. Given a target model that we want to learn, which is solving certain promise problem, we say that this promise problem self-tests this model if for any other model solving the same problem, there is a unitary or anti-unitary connection with the targets. So what it means is that if we have two models solving the same problem, promise problem, under the assumptions that we had, which is the dimension assumption, then the following must be true. The channels implemented here must be unitary equivalent to the gates that we wanted to self-test. States must be also unitary equivalent with the same unitary gauge, and so is true for the measurements. Now, this is what the self-testing is in the sense of foundational self-testing. And these unitaries you cannot get rid of, right? Because this is the gauge freedom that you have in the sense of the unitary freedom change of basis, global change of basis, what you call your basis, pretty much. So that's a goal. Now, let me tell you the first result. So this is the, we want to self-test here the pi-half pulse gate, which is an S gate that we've been talking about. But now I modified the promise problem a little bit because I want to have a shorter circuit, the shortest experiment possible for this kind of self-testing. So my promise problem looks like this. I either give an empty set or I give two instructions, which are S and S minus 1S, or the other ones, and I want them to be separated in yes and no answer. Now you can see clearly that the qubit can still do this, right? So there is this self-testing, there is this quantum model that we can self-test using with this promise problem, and that's the first result. And classically, you need dimension is equal to 3 to solve this problem. And the first result is that if you pass this test in the regime of infinite statistics, you will be able to say that you indeed had the following starting state, unitaries, and the measurements implemented. Now, that's for the infinite statistic regime. Of course, you want to go ahead and make these things robust. That's the second result of the robustness. So this is a theorem which we call epsilon sound certification of this qubit model that we have. It says the following thing. Let this be a quantum, one qubit quantum model, which is some experimental state, two separate channels and measurements that passes one run of protocol with the probability at least 1 minus epsilon when it tries to solve the promise problem. So you're running this protocol and you have a quantum model which passes this protocol with the probability at least 1 minus epsilon. Then there exists unitary V such that the following thing is true. Your channel, whenever you press the button S, is in average gate fidelity at least this close, and the scaling here in epsilon is linear, which is the best known so far, to the best of our knowledge. It's the scaling which is linear into this probability of failing. And you get the same result for both gates, because we had here two channels, so we get two separate gates. And the same is also true, you can claim the same things for the quantum state and the measurement that you are implementing. So this is the fidelity norm and the infinity norm for the measurements. And the average gate fidelity is just defined with the overlap between Choi states of the target and the desired channel, the target and the experimental channel. Yeah, so this is, in our opinion, very interesting results that from very simple tests like this, you can turn into the linear lower bounds into the fidelity of the gate. And you can think about this of being also device independent, right? All we are testing is now inputs and outputs under the dimension assumption. So I should put there semi-device independent, but people usually put under semi a lot of other stuff. They trust measurements or I don't know, everything. And that's why we didn't want to be confused that we start our states or measurements. Now, you can go ahead and turn this into the sample complexity result. And the corollary of this theorem is that protocol 1 is epsilon certification, which is sound and complete certification test for this model, simple single qubit model, with respect to average gate infidelity with n independent samples with the confidence at least 1 minus delta, where these samples need to grow inverse linearly with the infidelity that you have in your experiment. Now we still have big O here, and you can ask, okay, this is now big O notation, but what are this is the worst case scenario, what are the actual numbers there? Because if there is, I don't know, 10 million sitting, then well, maybe that's not good. And for this, of course, you can do a lot of numerical tests. And these are the tests which show you, so this figure shows you the dependence between average gate infidelity and probability of failing a single round. And we have tested now for different noise models, where you see that these noise models concentrate here. So there is certain unitary noise or depolarizing noise, or different stuff. I think totally 10 to the power 8 different models, random models were tested, individually 10 to the power 7, but Jan tested it so many times that you can, he was trying to catch the worst case here. And this line is the worst case line, and the dependence here is pretty much, what you see is that you have to test it 5 times epsilon minus 1. So it's pretty good in the sense that if you want to have this kind of confidence, and if you have 99% fidelity, then you have to repeat the experiment 2,000 times, pretty much. Now, if you want to have the state-of-the-art confidence, of course, you have to repeat it much more times, but it still scales linearly in the number, in the infidelity, which is the best in the sense that it also gives you the device independence guarantees about your fidelity. Okay, now this was for a single qubit S gate. People say, oh, this is only a single qubit gate. Well, can you try harder? We won't accept your paper because, you know, there is all these other methods like randomized benchmarking and this stuff, which gives you information, which is in the end, not telling you much, but well, you can still do it for n qubits. So can you now do things for the n qubit? And first step is, of course, to generalize the single qubit results. And for the single qubit results, you have to have new promise problems, of course. And now this promise problem corresponds to, so you might need a longer depth circuits, and every time you can think that S minus 1 corresponds to, you want to test S gate and S minus 1 gate, which is just S dagger. H corresponds to Hadamard, T is the T gate, and you can separate them between yes and no answers. And you can show that these kind of sequences just start somewhere on the Bloch sphere. It walks around the Bloch sphere and always ends up either in yes and no answer. So you don't have to gain this statistics in order for you to do the self-testing of this kind of model. And our result is that promise problem that you see here, and the protocol 1 indeed self-tests this single qubit universal gate set. So you can show that the only thing solving in the qubit this problem is using the correct unitary gates. Classical dimension here also just grows, it's a treat. So treat can use to solve this nasty problem. You can try to make the dimension separation larger, of course, by adding more sequences, but at the moment we are investigating whether that makes sense or not to have higher robustness into the epsilons. Next thing is an entangling gates. And this is a trickier business, much more trickier business in the sense that, well, you have a quantum device on which you are executing certain circuit. And now in our model, the quantum model, we don't assume anything about the tensor product structure. Because we have a total dimension assumption. You don't want to assume that you have 5 qubits, but in our model we assume that every time you press a button, it executes something on the entire Hilbert space. Because you cannot eliminate crosstalk a priori without having done the certification test. So the challenge here is ensuring or putting back from your promise problem results tensor product structure from just observed, I say here statistics, but it's really the observed responses to the promise problem. And here we have also a theorem that there exists very nasty looking promise problem, which I don't put on the slide, which indeed can self-test CNOT gate under the dimension assumption of 4. So it builds on top of other certification somehow. Now that you have already certified that you had S gates, now on top of that you can build the entangling gate. And what's not trivial here is that you still want to have deterministic answers only. So you have to walk in the space of, you have to design the circuits in a way that your answer is deterministic all the time, but you still learn that there was an entangling gate. But this is possible to do because with the S gate and Hadamard gates, you have change of basis. So now you can think that you can still get the deterministic answers only and learn that there must have been an entangled gate somewhere in between. And then you really self-test that this was CNOT gate, still up to the same unitary gauge. Another tricky part is that you have to keep even though you self-test these gates maybe individually, you have to have them in the same circuit to connect their unitary gauges together. And that's a tricky accounting that Jan has done in our group for a few months. So if you want to know details, he's the one to go to. And the final theorem here is that protocol 1 self-tests universal gate set. So that's what I was mentioning. If you separately do this and separately do single qubit one, you have to still bring them together, because otherwise you're doing apples and oranges, right? In one case you have the CNOT gate self-testing, but up to different unitary, and here you have single qubit gates with the different gauge, then you cannot put them together. Yes, now the comment here is the number of tests here grows actually exponentially in the number of qubits, but this you cannot get rid of. I mean, if you want to learn what's happening inside this kind of a structure with only yes-no answers, you have to ask too many questions, because the Hilbert space dimension here is 2 to the power n, and you want to say exactly which model you are working on here, you need to ask quite a lot of questions. On top of that, a lot of questions are wasted in the establishment of the crosstalk. So if we have n-qubit quantum gate, we let it first qubit interact even with the last qubit. We assume that there could be such an interaction when you press the button S1 to self-test the single qubit, first qubit iteration. And then you have to do all these many tests to make sure that it is indeed working properly, and the first qubit test is doing only it's close to having tensor product structure only on the first qubit. Now, if you have additional assumptions here, which are reasonable assumptions, let's say light cone assumptions that the first qubit is not talking to the last qubit, if you have, 200 qubits in the first iteration, if you know your connectivity, you can throw these assumptions on top of your promise problem and say that, okay, this I trust at least, and this way you can reduce the sample complexity or the number of questions that you have to ask. And that's something that we are preparing also at the moment, because we haven't rigorously put in the connections yet between promise problems and quantum system quizzing. And now we are trying to optimize the number of questions you have to ask a quantum computer in order to have a high separation between classical versus quantum systems, and also just optimize the number of questions that you have to ask here in order to gain the confidence into your devices. Okay, then I come to summary. I hope I motivated you that unfortunately literature, or fortunately for us, doesn't yet provide certification methods which are complete, which are sound, sorry. It only gives you completeness promise. So it doesn't give you the soundness results, that you can infer the quality of gates from the data that you get from a quantum computer. And we think we are not aware of anything else, so please tell us that if we are wrong, that we gave the first sound and spam-free method for certification, something that indeed gives you the guarantees. And it's promising in the sense that for a single qubit gate that we had, you have inverse linear scaling in the infidelity and sample complexity. So this is something that you want in order to benchmark your devices on the fly. You don't want to have to make too many measurements to learn what your quantum computer is doing if you want to learn the drifting in your pulses. And we have soundness proof for self-testing we call it memory-bounded quantum computers. But this is for the infinite statistics regime if protocol passes all the time, and we haven't yet turned it at all into the epsilon greater than 0 or the robust certification tests for the other gates that I presented. We only have for pi-half pulse. So with this, I want to invite you to maybe discuss these ideas and see how you can prove these things for more general gates. Things are not so easy there, because the way we did it for pi-half pulse, it was pretty much using the heavy machinery of going into the channel, taking the channel and looking at its Choi matrix and then bounding each of the coherencies into Choi matrix for just looking at the statistics. we don't want to do this for every new gate. Like, that's not sustainable. There has to be certain methods there. We have a couple of ideas which we are happy to share and discuss with anybody who wants to work on this stuff. And the bigger idea also here is to have some kind of integration of this promise problem into quantum algorithms. In a similar spirit of what you do in the device independence key distribution. Randomly, sometimes you test that you are violating a Bell inequality, but randomly, Alice and Bob use their rounds in order to establish the key. And if you see that many times from your random trials you violated the Bell inequality, then you have your confidence that these independent rounds worked nicely for the key distribution. Here, you can start to play a similar game. You are talking to a quantum computer. Quantum computer does not know whether you are sending it quizzes or you are actually working on your algorithms on the random qubits that you are working with, subset of qubits, and your goal is to test it, tell it to measure it sometimes, and if it gives you correct answers, maybe you can turn this into the statistical certification of your quantum devices without too much overhead. Next thing is that, of course, we want to challenge assumptions. The dimension assumption, we are a bit talking there already, how to challenge the dimension assumption, but what's trickier is to challenge the time independence assumption, because definitely it will be happening in your experiment that third time you press an S gate might have a higher drift or error than the first time you pressed it. So somehow maybe you learn your device or you integrate certain noise model into your device, and with this you can use such certain integration of the noise that let's say you get square drift for every press of the button. And with this you can learn something more about certify your devices better. But these challenging assumptions at the moment is something that is also widely open. And last but not least is that the devices, the methods that I talked about, randomized benchmarking, gate-set tomography, and other methods, they are not bad methods, but they're not defined for certification. They're defined for characterization of devices. But characterization methods, when they're used for certification, they don't give you good answers. But now if you have a rigorous certification method, if you know that certain things are already working, then on top of that you can do characterization using RBs and other stuff and get the information which you can trust. So this is the way that we are thinking that our certification method will aid the community to do the rigorous characterization later, knowing that their assumptions are fulfilled before they start the experiment.